Let's continue on a final exam. The same year final exam, the first question. The Turkish video is already here, so let's read it first and continue. Final exam, the first question in English. Let me find it. Yes, here it is. Okay, let's read and solve it as fast as possible. The no-load characteristic of a three-phase star-connected two-pole round-rotor synchronous generator is given as blah blah. There is no saturation and machine is assumed linear. Okay, let's write what we have done so far. No load curve, but it is star connected generator. Two pole means there is only one pair of pole. Round rotor synchronous generator, star connected round rotor synchronous generator. Yes, having one pair of pole. No load curve is given as 100 times field current. We don't know field current, but the relation is given. Remember no load experiment, no load or open circuit test. Sometimes we said open circuit test, sometimes we said no load test or curve. It is the relation between induced EMF and field current. In fact, in reality, it was something like that. There was a little bit hysteresis. Here is ER. But in the question, the relation is given linearly. There's a constant coefficient. The steep of the curve of the line is 100. So EF is equal to 100 times IF. That is the no load curve given in the question. Star connected two pole, blah blah, synchronous generator. Okay, the synchronous reactance of the generator is 2 ohms. Ladies and gentlemen, XS is given as 2 ohms. Let me write, okay, 2 ohms, and have a negligibly small resistance. So array is neglected. Array is neglected or omitted. Okay, the generator is operated on a grid. Having such a voltage, frequency and phase number. Okay, on grid there is on-grid operation, The network or grid has some parameters. Line-to-line voltage is 400 volts, 50 Hertz, yes, and 3-phase. Okay, those are the network parameters given. Machine is operated parallel with such a network. Total mechanical losses, which are, you know, total mechanical losses are made of frictional and windage losses, have such a value. Mechanical losses are 2101 watts. Okay, during this operation, the generator is driven by such a torque. Okay, while having a value of 325. Machine is a generator, synchronous generator. Here is a turbine. Here is some mechanical input power. There is a torque applied to the machine which has such a, as I remember, 325 Newton meters. That is the mechanical applied torque. And here's speed of shaft, angular speed of shaft, which is synchronous speed. And machine delivers some power. Here is infinite bus grid, national grid, has some values like this, constant values. Okay, let's continue. What should the excitation current be of the generator in order to deliver a power with a 0.9 lagging power factor? Okay, ladies and gentlemen, as you see, here's a power. Because you insert some mechanical input power, that power is converted into electric power. To make this, you need a magnetic field. There's a field current. Depending on the field current, there would be some reactive power exchange, and it is given power factor of 0.9 lagging. 0.9 lagging. Houston, adjust field current properly to have such a power factor together with such an active power. It looks easy, but you should know apply some equations. Okay, the time is getting consumed, so I'm in a hurry. Now, what is happening here? You apply some mechanical input power in terms of torque and mechanical speed, angular speed, and then here are some mechanical losses. After they have loosened, here's a converted power or induced power, that power converted into electric power. Then here would be some copper losses, but since there is no armature resistance given, it is neglected. There is no copper loss, so here's electrical output. Those two parameters are equal, so let's write electrical output is equal to converted power, and it is also equal to summation of the subtraction of losses, mechanical losses from applied mechanical input power. Let's do it, ladies and gentlemen. We subtract mechanical losses from mechanical input power, and we will have electrical output or converted power. Now in this case we need electrical output, but computer science that mechanical input power is not known yet. Mechanical input power is equal to torque times angular speed. Angular speed. Okay, it is not known right now, unknown. Angular speed 2 pi ns over 60. Again, ns is not known. let's calculate NS, which is 60 F over whole pair number. So let's check it out. It must be 314. Yes, we are in the correct. That must be 3000 RPM. Yes, and the angular speed is substituted here. What is the torque? Torque. I don't know, but it looks known. No, here's something confusing. Torque, applied mechanical torque, is given in the question, 325. Torque mechanical is given 325 Newton meters. Houston. Here is the TM, mechanical input torque. So mechanical input power is equal to such an output, such an input watts. If you subtract mechanical losses, you got electrical output, which is purely 100 kilowatts, almost purely 100 kilowatts. That's it. Now, ladies and gentlemen, we know this. We know power factor. Okay, here's a generator. Here's the generator. Apply something like that, delivers such a power at a power factor of 0.9 lagging. Power factor 0.9 lagging. So line current can be calculated. Power delivered to three-phase grid is square root times line voltage, line current, and power factor. So line current is equal to power, which is 100 kilowatts, something like that, as you see. 100 kilowatts over blah 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 blah. Let's do it. Line current is equal to electric power across the terminals, delivered to terminals, over square root 3 times line to line voltages and power factor. Houston, power factor is not known, but it is already given. It was 0.9. Here it is. It was leading, is it? Lagging. Okay, let me take care. Lagging. Here's the line current, ladies and gentlemen, such an amperes. But machine is connected star or delta. Machine is connected star, so single phase current is equal to line current, the same value because machine has star connected. Also, single phase terminal voltage is equal to line to line voltage over square root of 3. That is approximately 231 volts, since star connected, star connection. Okay, now ladies and gentlemen, the question: to deliver such an active power, yes, but at a power factor of 0.9 lagging, together with some reactive power, but we don't know reactive power yet. what is the excitation current, which is field current? Field current relation is given here from the no load curve, so you should calculate EF first. EF first. What is the where is the relation coming from? EF is equal to V1 times I1 JXS. That is the equation. Array is neglected, so I haven't written it is here. All those are in complex form. I should calculate EF amplitude first, and then I know that EF is equal to 100 times IF. Then I will calculate field current. But again, do not forget to write phasor relations here. Let's continue. EF is equal to V1 single phase voltage times BB plus, I1 times, must be phasor, do not forget, J times XS. And J is unknown, which is a complex parameter having a value of minus square root of minus 1. And I1, ladies and gentlemen, what is I1? I1 has such a value, but it is just amplitude. So what is the power factor or phase angle? Phase angle is arc cosinus of power factor, beep, and then it is it has got such a radiance, but you should evaluate or assess it in degrees, whether it is convenient or not. Yes, it looks okay. The factor was lagging. Ladies and gentlemen, something needs to be corrected. Power factor lagging. Lagging phase angle must be negative. So I write here negative, make corrections, degrees, and negative due to it is lagging. Since it is lagging, we have corrected the sign of the phi. Now, ladies and gentlemen, now I change here. I write phasor equation. I1 times e to the j phi. That is the phasor equation, phasor value of the current. As you see, it has a negative angle. Arctangent imaginary over real makes a negative value. So I will substitute this value here and take it here. As you see, EF is calculated. EF has such a voltage. But we need a magnitude, RMS value, so we got the absolute value, RMS value, magnitude. That is the magnitude of EMF. We need a field current. Field current is EF over 100. It is already given here. The relation, no load curve relation is given. So required field current can easily be calculated. Excuse me, DC has no phase difference, so this guy must be magnitude. Okay, that is the required DC current. That is the required DC current. When you excite machine with such a current, ladies and gentlemen, here's a generator, synchronous generator, delivering some power, let's say 100 kilowatts. And then here's an excitation current. When you adjust excitation current, let me change color. When you adjust it properly, reactive power would be 0, having full ohmic operation. Reactive power would be lagging. Reactive power would be reactive power will be leading or would be lagging. But here in this case, in the question, it is given as 0.9 lagging. 0.9 power factor is 0.9 lagging. That means there's a phase difference which is positive and reactive power must be negative, but in the question the excitation current is asked. Excitation current is equal to EF magnitude over 100, that is coming from no load curve. That is the no load curve. To get such an EMF, you need such an current, and if you excite machine by such a current, you deliver some leading reactive power together with that active power, resulting such a power factor. Let's check it out, our results with the given answers. Yes, as you see, phase angle was minus 25. Yes, it is. The current is 4.699. Yes, it's it. It is. We got the solution. It is easy, but you should consider everything 360 degrees. Each part of the topic must be known. You should assess no load curve. You should evaluate phase angles, whether they must be positive or negative. You should use phasors properly, and you should make some conclusions. For example, here in this equation, although we have not discussed here yet, the delta looks positive. Delta must be positive because it is generator, operated as generator. Okay, that's the end of the question.